In this video, we will talk about what paths are. Okay, so I want to get right into an example, which says, for the following graph, is there a path between the pair of vertices? And if there is, find its length. I want to try to tackle this right away with an example before we actually define what a path is more formally. Okay, so is there a path from A to D? So if I look at my graph, here's A, and here's D. Well, is there a path connecting those two vertices that'll let me travel from one to the other? Well, no, because there's no like edge that lets me get from A over to this piece where D is. So, okay, there's no path. There is no path connecting A and D, unfortunately. But what about B? Is there a path connecting D to E? So sure, I see one right here connecting D to E. Awesome, that is one path. So the way I will indicate that is I will write that edge D to E in my set notation, D to E. And this is a path of length 1. Path of length 1. And the length just means, well, how many edges did I have to travel along to get from my starting point D to my ending point E? And, well, we had to travel along one edge. That's not the only path that gets me from D to E. In fact, another one would be, well, what if I went from D to F first? And then F to C? And then what if I took this loop around C? And then what if I went back to E? And then I went, oh yeah, and that's when I want to stop. I want to stop at E. Okay, so what if I did that roundabout way? So what if instead I went from D to F? And then after that, I went from F to C. And then I did C to itself. I did that loop. And then finally, only finally after that did I do C to E. So what if I did that? Let me give myself more room. Let me move this up over here to the side. Let me separate these two. That's a totally valid path. And this one has length. This one has length 4. We had to travel along 4 edges before we got to our final destination. Okay, and then what about, is there a path from A to A? Well, yeah. I could start at A, go to B, and then travel back to A along that same edge. So yeah, I can get there. I can go, oh, let's keep it in black. I can go from A to B, and then after that I will go B to A. So this is a path of length 2. Okay. And I think it's not hard to see at this point that, I'm just listing some of these paths, but there's many more. Like I could have gone from A to B, and then B to A, and then A back to B, and then B back to A, and I would have had a path of length 4. I could have had many, many more of these paths. I just listed a couple of examples. All right, so what is the formal definition? This says, if G is a graph and N is greater than or equal to 0. Okay, and I'm going to let V naught and Vn be vertices of G. So V naught and Vn, they're going to be vertices of G. What I say is, I say there's a path from V naught to Vn of length n if there are a sequence of vertices, V naught, V1, V2, all the way up until Vn. So there's some sequence of vertices from wherever I'm starting, V naught, up until where I'm ending, Vn. And there's a sequence of edges, E1, E2, up until En, kind of connecting all these vertices. And the way I write that they connect all of them is we say that the endpoints of edge EI are Vi minus 1 and Vi. Okay, that's the formal definition of a path here. So the new term I want to introduce now is we say that a path is simple if it does not contain the same edge twice. Okay, so these two paths that we had listed from D to E, well, those are both examples of simple paths. So this one was simple. This one was also simple. We didn't repeat any edge twice. But the path we had from A to A, it did traverse the same edge from A to B and then back from B to A. So that one, unfortunately, was not simple. That was not a simple path. Okay, so I want to end this video with a practice problem for you all to try, which is I want to make a simple path so I cannot duplicate edges in the following graphs that end up traveling along each edge in the graph. So it's got to be a simple path, and it's got to travel along all of the edges in the graph. It doesn't necessarily have to start and end at the same point, but it does have to hit each edge. This is something called a Eulerian path. Okay. So I'm going to give y'all 3 minutes to try this. And each of these, can you trace out a path that will cover each edge? It's got to be simple, so I can't duplicate the same edge. All right, so hopefully you did that. Hopefully you paused the video to try it. Let's go ahead and talk about, possible solutions for this. So there are multiple possible solutions for this. So, maybe for the first graph, what if I started at A? What if I started at vertex A? And let's say I started traveling to vertex E. So what I'm going to do is I'm going to start to label the edges that I'm traveling along. So this first edge that I traveled along, I'm going to number that 1. And then maybe from E, I go up to D. I'm going to call that 2. Let me just trace out the path first, and then I'll label the numbers. So I'll go from A to E, and then E to D, then D up to C. Then I can go to B. Then I go down to A. Then I can go from A to D. It's totally fine for me to visit the same vertex multiple times. Nothing was said I can't go to the same vertex. I just can't travel along the same edge multiple times because it's a simple path. Okay, then from D over to B, and then from B over to E, and I've traveled along each edge exactly once. Okay, so let's just number those edges. So now from D, I went to C, that's the third one, and then to B, that's the fourth, and then down to A, that's the fifth. And then from A up to D, that was number 6. D over to B, that was 7. And then B down to A, that was number 8. And that got it covered. Maybe the next one's a little harder just because there's more vertices and more edges. Again, there's multiple solutions to this. If you had something different than mine, that could totally be fine. There are many ways to do this. Okay, so what if I started at C? So maybe I go from C to B, and then B to A, and then A to G, and then over to F, and then over to E, and then I go up top to D, and then I go to C. So I got all the outside part. Let's do the inside part. So I'll go here, and then I'll go down, and then diagonally up, and then down, and then right. And I've done each of the edges exactly once. So if I number those, C to B was 1, and then to A was 2, and then over to G was 3, to F was 4, to E was 5, to D was 6, to C was 7. Now I got all the outside part. From C, I think we went over to E, that was 8. And then we went down to G, that was 9. And then we went up diagonally, that was 10. And then we went down to A, that was 11. And the last one was I went up diagonally to E, and that was 12. And then we had all of them. And there we have it.